Hi everyone, welcome to our event. This event is brought to you by DataTalksClub, which is a community of people who love data. We have weekly events, and today is one of such events. If you want to find out more about the events we have, there is a link in the description. Go there, check it out, and see all the events we have in our schedule. Do not forget to subscribe to our YouTube channel. This is very important. This way you will get notified about all our future streams like the one we have today. And last but not least, we have an amazing Slack community where you can hang out with other data enthusiasts. So all the links are in the description. And during today's presentation, you can ask any question you want. There is a link, pinned link in the live chat. Click on that link, ask your questions, and we will be covering these questions at the end of the presentation. And this is actually it from my side. Now, Ilya, the floor is yours. Please share your screen, and I'm really looking forward to your amazing presentation.
Thanks for the Alexey.
But I'm pretty sure it's going to be cool.
All right. So you right now should be seeing my main slide. Alexey, can you confirm you do?
I can see the slide. I can see speaker notes too. I don't know if it's intentional. This is right now is just a slide.
Actually, you should see presented.
Just a slide.
Let me try again.
It was good. Like at the end, it was good.
Because I expected to be like without speaker notes. All right. So can you say do you see now the full screen? Or do you see?
I just saw the full screen and now it switched to speaker notes again.
All right, then looks like it doesn't work, and I will proceed with the
It works.
Mm-hmm.
Right now it works.
Okay, good. So let's start. I'm going to talk today about AI Mathematical Olympiad, which was hosted on Kaggle. So this was the competition I took part recently, and it was very interesting. And I think I have some things to share with you about it. So we generally will speak a little bit about the intro to the competition, the problem, and how it was evaluated. Then I will dedicate some time about speaking about math problem domain in the context of LLMs, how they are trained to solve math questions. And then we will speak about competition baseline, model improvements, and some of the smartest ideas from winning teams, and we'll highlight some conclusions. I'm not going to talk a lot about my solution to this problem. So my team got the silver medal, and we got in 2% out of 2,200 teams, so which was nice. But yeah, I want to make this talk of more general introduction, technical introduction to the math domain, rather than discussing like very details of my solution. But if you would be curious, we can later have a chat about it. Let's talk about the competition. But before that, let's speak about International Mathematical Olympiad, which was the inspiration for the host to make this competition. So this is the Olympiad, which is held every year. And the goal is to solve really hard mathematical problems. So if you can solve problems from here, you are extremely smart. And this is very well-known competition among mathematicians. And it's a big honor to be here. And so actually inspired by this competition, so XTX Markets, a trading company from London, organized AI Mathematical Olympiad Prize, which was with the goal to actually develop models that can solve this kind of problems similar to IMO. And this competition was already held twice. The first one was 1 year ago, and the second one came out recently. And this competition has quite a big prize with total of $10 million. There is like some details about how it is being distributed, but I believe that already like half of the prize was distributed during these two competitions. And what is the data here? So for training data, there was 110 problems from different domains of mathematics. And it was told that organizers were really working hard to make sure that problems are really AI hard, and they will make sense in order to train state-of-the-art mathematical reasoning models. So the answer to each problem is an integer, and problems are formulated like in the classical LaTeX format. And yeah, so like they're supposed to be hard even for the current state-of-the-art models, because organizers were trying to run them using like ChatGPT models and some Claude models and so on. And that was the direction how to design problems for the competition. And this is the example problem. So we don't need to go into details here. So I will never solve something like this, I think. But just wanted to give you an idea that how hard it can be. And we expect AI models to solve that stuff. And from the evaluation perspective, it's just simple accuracy. So test leaderboard has 50 hidden problems. They are decontaminated and they are not available publicly. And there is also public leaderboard. And it also, you can see here that in the end, top teams had slightly above 30 solved problems out of 50. And what was also interesting is that this was a code competition. So in order to submit your predictions, you need to actually submit the code. And then there is Kaggle inference server, which runs your code versus test private data. And for example, if you have some issues in your code and it will fail, so you will not get the result. There was some dedicated GPU, both for experimenting and for inference. So when you submit your code, you can set up and realize that you will have this amount of GPUs. And also there was a time limit that your pipeline should finish in 5 hours. And again, for example, if you use very slow and very big model and you will not finish in time, your submission will not count, right? And so this was actually very encouraging for people to think not only on scientific issues, but also to think from the engineering point of view, how to make this faster. And now let's speak about math problem domain in general. So basically how to introduce math skills to the model. So there are 3 stages, which first is pre-training. So you know that LLMs are pre-trained on very big corpuses of data. And together with general knowledge data, you can introduce math-related text, code snippets, like some other stuff, and also including synthetic mathematical data, which now also can be of really high quality. You then, during your post-training stage, apply supervised fine-tuning, mostly with using chain of thought and two integrated reasoning patterns. We'll speak about this soon. And after that, you may want to use reinforcement learning to further align model to desired properties. And we will also talk about what kind of properties you may want to have here. Basically, math is very beautiful and interesting domain in the context of LLMs. It is known that LLMs now can solve really hard problems, like for this competition, for example. But it is also known that LLMs struggle with sometimes simple problems. And why this actually happens? Basically, because LLMs do not have calculator and a symbolic reasoning engine, and they handle math symbols not quite well. For example, sinus of x is tokenized in Llama model to 3 distinct tokens, right? So model doesn't understand that this is a single entity. And so there is a built-in randomness that can, the model makes up after regressive decoding. It can hallucinate or maybe go into another direction, and then your solution will not follow strict mathematical rules. And so it's also known that models just in general are not inefficient in expressing iterative solutions, which also quite common happen in mathematics. And now let's talk a little bit about tool-integrated reasoning, because this was even a year ago from the first AI Mathematical Olympiad Prize winning solution, an important paradigm of how to approach this kind of problems. So on the left, you can see that there is a chain of thought solution. Then model makes some reasoning and then provides some answer, which is not precisely correct. While on the right side, you see that there was some code prompt that we prompted the model to write a code to solve the problem instead of actually reasoning and solving that. And after the model generates a code, we can call Python interpreter and actually execute this code. And this can give us, as we see, a correct solution. So this idea of introducing some tools, for example, Python, some other like mathematical tools to help us solve complex mathematical expressions can really boost our accuracy. This idea was the winning idea of last year AI Mathematical Olympiad Prize. And of course, it was also utilized this year. And we can see that like both chain of thought and so-called program of thought or tool-integrated reasoning helps solve mathematical problems. But for some types of problems, you see that it's also interesting to look on distribution of accuracy between different mathematical domains. For example, models are really bad in especially chain of thought in solving polynomial equations, or like some probabilistic problems, or like combinatorics. And for some like arithmetics models like are better. And also there are some domains and chain of thought works really bad, and program of thoughts with tool-integrated reasoning really helps, and it makes a difference. And it is also interesting to learn what kind of issues may happen with tool-integrated reasoning, because it's also it's also not perfect. For example, so this is an error with like classic chain of thought, sorry, not integrated reasoning. So we have a problem, and we see that there is a so-called value grounding error. Then model like precisely generate logic what has to be done, but it assigns variables incorrectly, and it's not grounded, right? And another type of error is incorrect mathematical logic. For example, in this case, model didn't understand that like subtraction should be done like from the other side, and it makes up a bad answer. So this helps, like this shows some fundamental issues with like model mathematical reasoning, and it's hard to solve, but it is good to understand which kind of errors actually happen in mathematical reasoning, and it can help you to direct your research to solve this, at least partially. And now, once we know that we can approach mathematical problems with chain of thought solutions, with tool-integrated reasoning solutions, and with just using models which were pre-trained on mathematical data, let's move now to discuss the baseline. So you usually take some pre-trained model, which is known to be good in math, for example, DeepSeek models or Qwen models, and you use some chain of thought or maybe tool-integrated reasoning code prompt with integrated Python interpreter to solve it. And then you can use majority voting when you do multiple samples with different parameters like temperature and so on. And you extract answers with regular expressions, and you take the most frequent answer. So this is the ultimate baseline for this competition. It gives some okay accuracy, so it works fine. You can solve from the public leaderboard maybe 20 problems from that, maybe a little bit less. But this has very high latency, which is mostly impacted by number of generations, number of reasoning tokens, and actually model size, right? And basically the next, so all the improvements were to actually tackle these issues. We want to think how we can like reduce the latency, because if we get this, like we can use maybe stronger, bigger model, or maybe some like longer reasoning if it helps, or something else. So a lot of ideas from the competitions were tackled to solve these challenges. And these challenges can be solved during post-training. So again, you take some base pre-trained model, for example, DeepSeek or Qwen, and you can do, for example, supervised fine-tuning on high difficulty math problems, and it can help you adapt to this domain and solve problems better. There are a lot of data sets which can help you with that. So data sets which were generated like some with synthetically from like some of the best open source models and the state-of-the-art models like ChatGPT, Gemini, Claude, or something. And this is considered as high quality data, which you can fuse a filter to maybe include some of the hardest problems and so on. And you also can train on top of that preference optimization. For example, you may want to do this to reduce output length. Reasoning takes a lot of tokens, like 10,000 tokens, 16,000 tokens, and this is really a lot. And maybe there is a chance to reduce this length, but to preserve accuracy. So maybe it's possible. And yeah, so as I already said, latency is mostly impacted by like these factors. And let's see what we can do with that. There is very nice research work from UC Berkeley lab, NovaSky, which created a model like by design similar to OpenAI O1, a reasoning model, and showed that it is possible to reduce so-called model overthinking. So to reduce reasoning length, but to preserve accuracy, right? And they did that by the fact that they created a lot of problems and like answers using like some of the state-of-the-art models. I think they used Qwen 32 billion instruct model. And then for each problem, they analyzed, for example, we have multiple samples. We have the longest sample, which is correct. We have the shortest sample, which is correct. We have some samples which are incorrect. And we can make up preference pairs. For example, given 2 correct answers, one correct answer has 16,000 K output length, and another correct answer has maybe only 8,000. And the latter would be preferred because it's much shorter and more concise, right? So, and once you generate these pairs, you have a labeled data set, and you can run preference optimization to actually align model to produce more concise solutions. And they showed that when you have even quite a small compute budget, you can get very good results with like not a lot of data and this smart strategy. And actually, a lot of contestants of the competition were motivated and impressed by this research, right? A lot of people were using that, including our team. One more thing of how you can optimize the model is to introduce some early stopping strategies. Maybe you don't want to train model at all. Maybe you don't have GPUs or something. You still can do something to make a better solution. One smart idea is to actually to stop your generation once you meet a think token. If you look on guidelines how to use models like DeepSeek or Qwen, so they add special tokens think in the beginning and end of the reasoning. And usually the answer is inside the thinking. So once you meet this closing special token, you can stop generation and use regular expressions to extract your answer, because the remaining part would be something maybe redundant, yes, just some flowery language. Or maybe model will go to do some double checks. Sometimes it can be beneficial, so we will talk about it, that sometimes model make like multiple reasoning steps, but not always you really need that. Yeah, and another idea from one of the winning solutions actually was they discovered that actually if they identify first successful executable code or first answer, they just stop the generation because most likely it would be a correct result, especially given you use majority voting and you aggregate results from multiple generations. This was producing already like good improvements. Now let's talk about number of generations. Let's say by default you want to use 32 generations. So you need to call for each problem the model 32 times, right? So this is very time consuming. What we can do to decrease that? So very simple thing is to so because we use majority voting, we know that the most frequent, so if some answer is met more than n divided by 2 times, so the more than half of the times, we know that this is definitely a majority. So it will not, we can stop generation once we see some answer with n divided by 2 count, because no other answer can change the final solution. So this is a very simple idea, which was very helpful for some of the especially easy problems. Then your model generates one result from lots of passes. You just don't need to run them more. And also the model size. So people were usually using here models like starting from 1.5 billion up to 14 billion parameters. I think that bigger models were not fitting the memory requirements of available GPUs, which were for each GPU. And also what was popular is to use some distilled or quantized models. For example, Qwen model, which was distilled on DeepSeek R1, like the biggest DeepSeek model. And also from the quantization point of view, activation-aware quantization was the most popular choice, and we'll talk a little bit about this soon. And also, so we have several stages where we can optimize the model. We can optimize model using post-training, like by making generation length shorter. We can use some early stopping strategies, and we can also analyze various inference frameworks and make sure that we use them as good as we can. So the GPUs utilized in the best way, and some other features, for example, like continuous batching, page attention, and some other stuff. So basically, if you are curious about inference optimization, I highly recommend to look releases, documentation, and details of these frameworks. So there are a lot of very smart ideas, and the field is moving quite rapidly. So for example, this is the slide where guys were showing how two different frameworks differ from the throughput perspective, and also from what's more interesting for me, from the model initialization time, because on Kaggle, on the submission, you need to first initialize the model, and you see that using LM deploy compared to VLLM, these guys were able to get some time which you can utilize for prediction when you have limited prediction time in total. From the inference perspective, so for example, it was interesting and useful for me to read various release details of the LLM library, which I used. And you just read and go and see what they're doing. And I found out that they introduced the version 0.8 V1 engine with lots of optimizations. So you just switch to that and it worked 10-20% faster. Also, there are some experimental features like chunk prefill in VLLM. So you can read here with the link a little bit more about that, which also was speeding up computation a little bit. And also you need to make sure that you correctly use parallel compute strategies so that your 4 available GPUs are utilized as much as possible. And one more smart idea, which actually we used that. We also found out that first place solution was using that. So I believe that multiple teams came out to this independently, but this is actually very intuitive. And let's discuss what I mean by, I call this time-aware dynamic sampling. So we know that we have to infer 50 problems for 5 hours. So by default, we can distribute evenly time for each question, right? So it would be about 5 minutes for each question, plus some computational overhead for model initialization and so on. And this is how we get 300 minutes in total. We should be in time for that. And after predicting each question, we know that we can spend at most 5 minutes on that. But if we spend less time on that, we can, for the next time, increase batch size because we have remaining time, right? For example, let's say for first question, we are using 32 generations. So we did 32 samples and we took majority vote. We got the solution. Let's say we have remaining, I don't know, 2 minutes or something. This means that probably for the next iteration, we can make not 32 generations, but I don't know, a little bit more, maybe 36 or some more. And this can really help because maybe there would be some ties between two frequent solutions, and maybe this increased batch size, this increased amount of generations can help you to figure out the best solution. So you just make up a logic to dynamically increase the batch size when you have time, and this helps to improve accuracy by being in time based on your prediction limits. And now let's speak a little bit about the most impressive solutions. The first one is the third place. I really like this solution because it doesn't use any post-training at all. So like they didn't have any GPUs. They just used existing model. I believe it was Qwen 18B, which was distilled from DeepSeek, which was a popular choice for this competition. And the idea is that we may control the moment when we should stop the generation and like do not produce like further results. So we first take, let's say, 5 examples, 5 branches of generations. We generate first 4,000 tokens, and then we can aggregate the results. We see like whether there is already a majority vote or something. And like if no, we can continue and like duplicate branches and continue based like on that. And we again like computing majority vote after next 4,000 tokens. And like, so the guy found out that this strategy leads to better accuracy because the idea is that we really want to stop early because quite often, so the closer your first extracted answer to the beginning of your prompt, so the more it is grounded. It is known that model hallucinate much more than they have like long reasoning traces, right? So hallucination increases, and there is a chance that like later responses may be incorrect, right? So once you have majority voting and you have agreement between solutions like from first 4,000 tokens, it's already very confident information that this solution might be correct. So it makes sense to stop here. And that's actually was the idea that you can use pre-trained model as is and get the third place. Second place was very like hard working team. So guys was working on all steps of like optimization we discussed before in this talk. So they did reasoning-oriented training with supervised fine-tuning and direct preference optimization on top to reduce sequence length. They also worked on inference efficiency. So they were also analyzing frameworks and like making sure that they utilize it the best. And they also worked on some strategies to also to introduce some early stopping criteria to make sure that like further generation is pointless. And for example, then they used supervised fine-tuning. They found out that when you fine-tune model on problems and high-quality math reasoning trajectories, this improves accuracy. But as you can see on this graph, the average output length of your reasoning also like increases, right? So after that, they applied direct preference optimization, and it helped to control the length. So similar idea as I showed you before in the Nova Sky research, which was like initially proposed. Okay, and from the inference point of view, they used activation-aware quantization and 8-bit key-value cache quantization. Key-value cache is a thing. For example, you know that in order to make a prediction for a language model, you need to compute attention using keys, queries, and value matrices. And actually, you can like because LLM is after regressive model, you can cache previously computed keys and values. And for each decoding step, you can get the cache values, and this speed ups computations by far. So, and they show also that you can actually also use like smaller precision cache, and it also like has some drop in accuracy, but still works fine. And actually, yeah, so I really like the fact that in this competition, people were trying various quantization approaches, like post-training quantizations, and activation-aware quantization was the best performing tool here. And I wanted just to give a little bit intuition how it works and why it looks so impressive. So the idea, if you look on the paper, is that researchers found out that not all weights are equally important for LLM. So there are some hidden weights which dominate like the final prediction, while some other layers and weights may contribute much less. Yeah, so there is like very small fraction of really important weights, like up to 1%. And it's intuitively, you can think that you don't want to quantize these weights, because if you reduce them to smaller precision, you can lose some important information, right? So once you identified these weights, you want to leave these 1% of weights in higher precision, but less important weights, you can convert to smaller precision and nothing will actually change, right? And now the question is how to identify these important weights. And that's actually the main idea of the paper, is that you need to design how to do that. And guys are referring to the activation distribution instead of actual weight distribution. And the idea is that large activation magnitudes correspond to like more importance to actual weights, because they process more important features. And there is a process with like mathematical formulas, how to analyze the model architecture and weight structure and identify potential salient weights. So once it is done, you do not need any additional data. So there is in-place algorithm which analyzes model and makes up these guesses of important weights. Once it is done, you can just do some simple scaling of not important weights, and you get quantized much faster, but still very accurate model. There is a demo how to do this in Hugging Face. There is a library auto AWQ. So you can simply take your transformers model and apply quantize method and get a 4-bit precision model. So you can easily use this for production. And I believe this library right now is already integrated with VLLM. So this is production ready. Yeah. So feel free to learn more about it. And then once more, think about second place solution. They had quite complicated logic for test time optimization. What I liked here is that they use streaming output of each example. They try to aggregate them and also judge like whether they should stop or not. So yeah, you can read more about this. Yeah, so I'm attaching, like if you can see there are links, I'm attaching everywhere links so you can read more about the solutions. And now we're moving to the first place, so which was absolutely crazy. So guys from NVIDIA even published a paper about the solution. And let's see what they did. So they created a new data set, which is called Open Math Reasoning, which they also open sourced. They came to the Art of Programming Solutions, Art of Problem Solving forum, and extracted a lot of problems from like various forums. And then they synthesized solutions to these problems using best open source models. They applied some quality difficulty filtering and uploaded data set to Hugging Face, which was already which attracted a lot of attention. And they used this data set to train their models. And they use Qwen 2.5 base as a starting point. And they identified 3 types of tasks: chain of thought solution, two integrated reasoning, and so-called gen select. And gen select is an idea which I actually find very interesting to improve upon majority voting. So they prepared a prompt that, like, given a problem and given some number of candidates, we're prompting the model to select the best candidate, right? So this is, you can think of it as like reward model based on multiple candidates. And they trained models on like all these tasks and got some like state-of-the-art models, which were like very precise. And to be detailed, for the Kaggle submission, they used a bit simpler model. For example, they were not able to use gen select algorithm on Kaggle due to inference time constraints, but they still developed various models and open source them so that the community could benefit from them, not only for Kaggle, but for some other tasks. And yeah, so actually they open sourced various models. You can find them on Hugging Face, the dataset and the paper. They also implemented some of the inference strategy, for example, like similar idea as I used with time-aware dynamic sampling strategy. And all of that combined helped them to get the first place, and which was very impressive. Okay, so now we can move to conclusions. There was a discussion actually after the competition that there was observed high variance in public scores, and Kaggle limited to 1 submission per day. And it actually was hard to understand like whether I'm moving like in the correct direction when I'm doing some research or not. So or it is just built-in randomness of LLMs. And after the competition, actually, there were like some discussions about evaluation on like, for example, Kaggle hosts were running evaluation once. So people got their positions, and contestants were discussing like, but maybe if we rerun, the standings will change dramatically. Maybe instead we should, I don't know, should have run this 3 times and average the scores. Maybe it would be more precise. And there was really nice discussion about that. And I liked that the competition hosts were very active and were like listening to feedback from people. They told that they were analyzing in details the distribution of trained data and test data, and they believe that the evaluation is precise, and the randomness should not contribute to drastic changes in the final standings. So I think that people more or less aligned on that, but that definitely sparked some like thoughts on maybe we can do something differently for the next iteration of the competition. Yeah, and actually there was quite a lot of discussions, and I like the fact that community also proposed some of the ideas about what is possible to improve for the next iteration of competition, or maybe not for this competition, but for other big competitions hosted on Kaggle, which uses LLMs and GPUs. So that was really interesting to read. So I like that community is active and helps to drive like the processes. Yeah, so the competition was very intense. I liked the fact that so you not only like solving particular problem, but also in order to solve this and find some research directions, I had to read some like papers, for example, about two integrated reasonings and the origins of that, to look for some other solutions, to look on different benchmarks. So this really helps to dive into the problem domain. And that's actually why I like Kaggle, and you are given some specific domain problem, and you have the time to become a domain subject domain expert here. So that's actually what happened in this competition as well. And some of the personally interesting ideas directions. So I liked very much 21st place solution. It used the classic logits distillation. When you extract logits from teacher model, you extract logits from student model, and you use specific distillation loss, which could be, for example, a Kullback-Leibler divergence between two distributions of logits of student and logits of teacher, and you train the model to imitate the teacher model. So that was nice. I really liked that the person succeeded with that idea. Also, I was very curious about improvements upon majority voting. So I was trying to do a gradient boosting ranking model on embeddings of problem descriptions and reasoning traces. I didn't have enough time to test and integrate this, but this probably can be possible for future. And also, I liked the idea of utilizing group relative policy optimization, which was popularized by DeepSeek team. For example, some of the teams used that, and it helped them to achieve high standings. And there are already some implementations, for example, Light R1, and this team also was competing in this competition. So it's nice to see these applications in like open source. I think that's it from me. Thank you very much. And I hope you enjoyed the talk, and feel free to ask me any more questions. Yeah, thank you.
Yeah, thank you. I was actually going to ask you about the presentation template and the slides. So was it just a template, or you use any AI to make it look nice?
It was just a template, so no AI was used.
Because I saw these demos where you get a boring slide and then the tool magically makes it more appealing. Because your slides are really good.
Yeah, thank you. I think that, I discovered, so I have here credits. I discovered this site, and I think this template kind goes from some of the research templates. So it's considered that you do some like maybe research proposals, or maybe overview of your paper or something. And like this one together with some others was working quite good for me. So it's like simple, minimalistic, yet beautiful.
And I just wanted to add my personal story. So for me, my first Kaggle competition was Alien AI Challenge. It was about, so you have a multiple choice question. So there is a question and 4 choices. And the challenge was to select the right answer. And it was like 2015, so like 10 years ago, when we didn't have any LLMs. I imagine now these problems would be so easy for LLMs to solve, because it was like an 8th grade test, a test for 8th graders. So without LLMs, it was a pretty tough nut to crack. But yeah, it was still fun. And for me, like I remember, like I just open it and look at this and, okay, what do I do here? Like life did not prepare me to to handle this stuff. And I know that by doing these things, you learn so much. So I assume like for you, by doing this competition, you learn so many things. And you said you finished in silver, right? What was your solution? What did you use?
Yeah, so we tried, so we had GPUs, so we had like a node with 8x Tesla A100. So we tried some training, post-training, like with supervised fine-tuning, but it didn't yield better results for us. So that was also like absurd. Like I saw that some teams, like, so a lot of teams were doing training, some like got some like improvements, some didn't. I believe like it depends on how you use data. Yeah. And for us, so like, so we are focusing on inference optimization. So like we did also some of the optimizations with inference framework to get the most from it. We did activation aware weight quantization. We did this time-aware dynamic sampling strategy. So we worked a little bit on system prompts. We used only chain of thought prompts, like no two integrated reasoning was used for us. So mostly, yeah, this kind of stuff. Yeah, and I think that's some early stopping for majority voting, yeah.
And to me, to be honest, like I'm not really into internals of LLM, so for me it doesn't tell much, but it's amazing. I assume you learned a lot about these things, like how actually LLMs work inside, because you needed to use these things in order to compete in this challenge, right?
Yeah, yeah. And you know, I think actually, so why for me, like, for example, preparing this talk, during preparation, I learned even more. So
Okay.
because I had to dive really deep into some like details, like to like, and this actually, I see so much value in this. Like, first, I hope like there is some value for people who like watching this and maybe like will get some inspiration. But also there is like additional value for me because I had to read really deep details about winning solutions, about what like reading forums, what other people were doing, reading some like even further details about quantization, some other stuff. And yeah, so this somehow like, I don't know, like very good summary for me as well. So that's why I encourage people like who participate, like to give like talks, maybe writing blogs, blog posts or something. So this help to summarize your like findings and learnings.
Yeah, definitely. Like, I have a few. We have some questions from the community, but I first want to ask my questions. When you were talking about supervised fine-tuning, there is a term you mentioned in the slide, is reasoning trajectories. What is that exactly? What is a reasoning trajectory?
Yeah, so it's basically so let me find this slide. Blah blah blah. Okay, so it's here.
Yeah, this one, yes.
So if you look on existing data sets, maybe let me see, like, do you see right now the Hugging Face page, right? Yeah, so you can see there is like some data set which was used like from R1 model, SFT data. You have here, so in the chat template format, you have some problem, and you have like model reasoning. So you see that this is in the think token, inside of the think token. Okay, so I need to find all prime numbers and positive integers, blah, blah, blah. So this is basically like model was prompted like with the, like this kind of prompt, and model which was trained like on a chain of thought prompt strategy can produce you the reasoning of high quality of how to solve the problem with the final answer in the end.
Okay.
And yeah, so this is just, so we want to train model on to actually do this kind of stuff. So we just use already a good model and try to like distill this knowledge by using this synthetically generated trajectories data.
What you show right now is the reasoning trajectory.
Exactly. Yeah, exactly. So you
Okay,
can
so
yeah.
which is the, I guess, a fancy term for there is an input to the model and this was the output. And now let's make
Yes.
sure that when we fine tune, we want our model to also produce similar output.
Yeah, so you can think that, for example, like before like reasoning became popular, for this problem, we could, so let's say we're asking this kind of problem of model, find all prime numbers, and model could just respond with the result, right?
Yeah.
But now model responds not only with result, but with like a lot of reasoning, which actually help to generate that solution. And we then like trying to extract the correct response. So like we need this reasoning because this is like model thinking, and we want to train on this data. Yeah.
Yeah, for me, the trajectory part of the term was confusing. So I thought it means some internal representation, maybe some, I don't know.
I think it was coming from some of the papers from Quen or from DeepSeek. Yes, it's where I copied it from. Yeah, maybe not so like widely adopted term so far.
Okay. And then a few slides later, when you talked about early stopping, and you stop when you see the boxed thing. Yeah, so here boxed. Do you prompt the model to put the answer in the box tag, or how does it work?
Yes, so this is like a classic LaTeX format. So you write a prompt to the model, like solve the problem, and like place your answer inside the box. So yeah, so that's why it is used. So this is the context of the competition. Sorry.
Okay, I don't want to take more of the time, but my questions. So I want to share my screen, and so you can also see the questions from the community. So there we have a few questions. I'm just going to read them out loud. So a question from Artur. Were you able to test smaller models and one LLM judge that could evaluate and score solutions instead of using majority vote?
We didn't use
a smarter way of aggregating solutions, right?
Yeah, so we didn't use LLM judge to compare to majority vote because it was it was just infeasible from the inference perspective to apply this. So as you saw, for example, first place solutions, they created so-called gen select algorithm, but they were also not able to use this due to latency constraints. So this was not a priority for us. I tried gradient boosting as a reward model, which is low latency model, and the idea was to actually to use gradient boosting as like to use majority voting as like candidate generators. For example, you get like top 5 by majority vote, and then you re-rank them by gradient boosting and get the top ranked. That was my idea because my like professional domain comes from recommender systems where you use this kind of candidate generation and re-ranking. That's why I tried to apply this here. Yeah. And the answering to smaller models, I think we tried both 1.5 billion models and 7.7 billion parameter models. They worked expectedly worse, even if you use higher amount of generations.
How exactly did you use XGBoost? What were the features? Embeddings or what?
Yeah, embedding. So I used Modern BERT. Modern BERT is a modern BERT architecture with a very long context of 8,000 K tokens, 8,000 K tokens, right? So you can encode problem description and you can encode reasoning, which I like was showing you recently. And you can compute question similarities. You can also compute some other handcrafted features. For example, how many times, I don't know, token weight, which means that model like reflects and maybe changes the solution is met in reasoning, and some other kind of like handcrafted features. And then you use this to rank the reasoning from the model. Yeah.
How successful was it?
It was, so I didn't like make a submission from that. From the offline accuracy perspective, it was nice. It was showing something like I think 0.9 ROC
Mm-hmm.
so yeah, it was
Mm-hmm.
from that perspective, it was nice, but yeah, I didn't have time to test it.
Okay. Another question from Artur. You mentioned Python as a tool was used in last year's solution. Was it used in this one as well?
Yeah. Basically, like if you go, so you saw that some of the like winning solutions had Python as a tool, and you can find some examples in the like Kaggle forums and like notebooks. You're just using, so it's very easy idea that you just use a library subprocess in Python, and you just with regular expressions you extract the code, then you call like subprocess.call, and you execute this code, and it produces some like parsable results, and you're fine. If not, you just like go further. Yeah, so you definitely can find the code how to integrate this as is.
And I think I know who is this Arthur. So we had a competition last year as a part of our course. We had a course about LLMs, and as a part of the course, we had a competition. It was also about solving mathematical problems, not like these ones, not the tough ones, but usual high school problems. And Arthur was taking part in this competition, and his approach was to take. So you get a mathematical problem, and then first you use an LLM to translate to create a solution with Python for this, and then you simply execute Python. So I think this is what Arthur used in that competition.
I think, Artur, maybe you can have a look on the Namina project. Namina, it was actually the winning solution from the last year. It is, yeah, NU.
I'm sorry.
Yeah. Like the second letter should be like U.
Nomina.
Yes, exactly. Yes. Yes. So these guys were like, if I'm not mistaken, the winners of previous like competition. So they were creating like models and also like popularizing like you see that Namina math model was like, so
Mhm.
yeah, it's also worth exploring them.
That's cool. So they won it, and then they got a bunch of money to continue research.
I don't know the full story, but
The
yes.
way around. Because it looks pretty cool. So if you're
Yeah.
passionate about something, then you find a competition, you take part, and then you say, "Oh, by the way, we can use your money, like if you want us to continue working on these things."
Yeah, sounds like a
And then
good.
they get support from all these companies. That's really cool. Okay.
Mhm.
Do you see options to use some of your learnings of the competition in your day job?
Yeah, actually, yeah. So I actually delivered like similar talk like in my company to my teammates like a week ago. And we also were discussing like ideas how to improve inference time strategies. So because we also have some like contextual problems, not math related, but some problems which are subjective, for example, and models make up different answers. And we need some smart strategies to like understand like when we can early stop and when we need to continue generation. So like yeah, teams are working on that.
Can you tell us more about what you do?
I work currently at Wayfair, so this is an e-commerce online retailer, like similar to Amazon. And we have a lot of problems related, for example, to product tagging when we want to extract from text description or maybe images some like attributes like material of the product, style of the product, and some other stuff. And these guys are very like subjective sometimes. So we also have like review summarization problems when you generate some like natural language summaries, like generate aspects and so on. So that's definitely all the areas that you can also apply some of the aggregation logic from LLMs and make it better.
I just realized that you guys might know each other. Um,
Okay, maybe. Okay, maybe I know.
yeah. Also, when you mentioned that some problems were better with chain of thought and some with TIR, I don't remember what TIR stands for.
Integrated
Perhaps one.
reasoning.
Sorry?
Tool
Two.
integrated reasoning, yeah.
Perhaps one could create a genetic model to decide which category is better.
Yeah. Basically, like if you look on the winning model of like this year team, so what they did, so they didn't use this in Kaggle, but for like for real world applications, you can use their model with three different types of like approaches. You can use chain of thought solution, you can use two integrated reasoning, or you can use this gen select algorithm. And it's possible to like wrap this idea into some agent when you can make have some another model which like makes a decision what kind of solution you should call to better solve particular problem. So yeah, basically, yeah.
Yeah, I think we don't have any more questions.
Mhm.
I have a question from me. We still have a couple of minutes.
Mhm.
So you at some point mentioned synthetic data, which was used for fine-tuning, right?
Right.
So how does it work exactly? What kind of synthetic data and where do you get the synthetic data from? Like, do you use OpenAI models to generate data and then train your model on that, or how do you do this?
Yeah. I think that it's mostly about synthesizing solutions from existing math problems when you have some like unsolved problems and or maybe solved problems with known ground truth answers, and you want to get from the models like precise reasoning so that you train. This is where you can like make synthetic data. Maybe you can also try to make up.
Sorry, I just want to make sure I follow. So you have a data set with solutions. So you have mathematical problems, and then you have solutions. And then you tell a model, okay, this is the problem, this is solution. Can you please reason to arrive at this solution?
Exactly. So you sometimes for a lot of problems, you have like problem description and you have just integer solution, for example, from some of the books or something, right? And you want to generate reasoning steps. This is one idea. Another idea, you can generate completely new problems, but you need to make sure that these problems are verifiable. And there are
Mhm.
mathematical tools when you can run and actually verify that the problem is correct. And this was also utilized by some of the teams.
Mm. And I assume for that you use, let's say you have a bunch of GPUs,
Mhm.
you can you can use a very smart big model for generating the synthetic data, and then later when you train the model for the actual competition, when you fine tune the model for the actual competition, then you use a smaller model, right?
Yeah. So that's actually the idea because DeepSeek R1 is like mixture of experts model with 6,671 billion parameters. So like, of course, less active parameters, but still you can use this to synthesize like reasoning traces and train a much smaller model like on this data.
And to be honest, to me, many of the terms you mentioned, like to me, LLMs are still kind of black boxes. I know how neural networks work. That's why for me it's not completely new, but still many things I have no idea how they work. So I felt a bit lost when you were presenting some things. So
Mhm.
I'm wondering, with these new things, like with all these LLMs, um, like, are there already resources that we can use to understand how they work better in order to, let's say, understand 100% of your talk?
Mhm. I think so. Basically, what you need here, you need some like strong basic foundational deep learning understanding of some like basic stuff, and then yeah, like you need to read some of the like must need papers
Mhm,
like about like so you are familiar with some of the modern theorems and some of the like research
mhm,
directions. Yeah, because some theorems are still not widely adopted. Sometimes people still like talking about like let's say fine tuning, but in LLMs it's like quite often now people speaking about post training. If
mhm,
like fine tuning can be different, it can be supervised fine tuning, it can be like continued pre training, which is also considered as part of post training. It
mhm,
can be reinforcement learning, so different kind of stuff. And I can
mhm,
understand that one can be a bit lost with that.
mhm. Do you know if there is a list of papers that I need to read to understand, or I
I
just
think
need to go into this rabbit hole and explore myself?
I think so. I think I definitely saw somewhere that like people were like doing quiz lists. Maybe I can look around and like send you the
Yeah,
data.
would be quite nice. And if you do this, I'll make sure to include it in the description.
Yeah. So deal. I can send some materials which were helpful for me.
Hey, I think we took a little more time than we planned, but Ilya, thanks a lot for the talk. It was really interesting to listen to what you presented us. Also, congratulations on taking part, even though, like, I don't know if you won any money, but I guess since you were in
Oh,
silver, probably not. But like, you don't do this for money. You do this for, like, it's a lot of fun to try new problems, learn new things. So I'm sure you learned a lot of things. So, and thanks a lot for sharing these things with us today.
yeah, thank you for like invitation. Like I enjoyed my time.
Yeah. And thanks everyone for joining us today. And yeah, I don't know when we have the next event. I guess sometime next week. So see you around. So have a great week, everyone.